All right, so stereo lithography. So I promise this is the last, probably the last week focusing on stereo lithography. So it seems really easy, right? When we first starting to dig in, just do exposure on your photoresist, right? But there's a lot of ways to do the modeling, and you have to understand how does the light intensity distribute on within the laser spot, right? And then you can have the calculation. You can build the model for exposure, and you can also find out the line width, the depth of the curing, right? The curing depth. So you revisit a little bit. Last Friday we were talking about the different scans, right? So this is called a ACEF scan pattern. It's supposed to be really accurate, clear. It's for epoxy and solid, right? So the idea is to find out how those accumulated exposure, right? Exposure energy within the line, right? If you go through multiple, if you go through one line, right? We already know the light intensity distribution within the line, right? But if you have multiple scans, right? If you have multiple scans, they will also affect this spot, right? The total energy at this spot. So this is to calculate your accumulated energy distribution, right, in this scan. Of course, you can use the same similar model. You can use the same methods to calculate that light intensity, the energy, right, with different kinds of scan. Not necessarily to be in this style. So we did that calculation assuming you have 9 scans, right? If you go beyond 9, the error will be really, really small. So they don't have that much impact to your to this spot in the middle, right? So you can go beyond that. I'm sure you can do the integration from negative infinity to positive infinity, right? This way, just considering 9 scans to make the life easier, so that it's easier to understand. And then you can get the total energy exposure, right? At that point. Right. So to summarize that, you can get this ratio, this cumulative energy, right, versus the maximum energy for one line, right? So you have this ratio is of course larger than 1, right? This cumulative energy is higher than this maximum energy, and you also have this factor. And we also did the plot in terms of this ratio in terms of how you scan the pattern, right? HS is the width, the width between 2 different lines, right? This is HS, and this is the thickness is the that's what it is, right? But it's the W0 is not the line width, right? It's not the line width. W0 is your half width of your light, right? Energy distribution, light intensity of the laser spot, right? This is the Gaussian distribution of your laser, right? So top down this is your laser spot, right? You will have a distribution of your light distribution, light intensity distribution of your laser spot. So through the cross section here, you will have this plot of this light, right? So this is half width of this distribution. This is W0. Okay. Now the line width. Line width is LW, right? We had an equation to calculate this line width. Remember? I cannot remember the equation, but I know how to derive them. So it's much more important to know how to derive those equations. So we got this. We had this plot, the EP over Emax versus the hash spacing over half width, right? So that means if you have this hash spacing smaller, you have a bigger impact of this EP, right? Make sense? So for this scan pattern, if you want to calculate your current depth or line width, right, you will have to consider this EP, now the Emax for one line, right? So your result with writing one line, the morphology of one line will be different with multiple lines together, right? This is 3 lines, this is 1 line. For 1 line, the current depth will be smaller than this 3 line writing, right? And so does this line width, because they have impact from other lines, right? So that's the basic idea, and it's really important to keep that in mind. Okay, so we had this calculation of current depth, right? The new current depth will be calculated. This is the current depth with one single pass, right? We had this equation calculated before. But if you have the new writing, right, with the pattern, right, with the pattern, we got this. We're now using the EP rather than Emax, right, for the calculation. So this should be ED0, right, for single pass. For single line. So ED0 is the current depth for single line. That will be DP line Emax slash over EC, right? So CD0 will be equal to DP line Emax over EC, right? Right? And this is CD1 is a line width, the current depth of this pattern, right? Right by the pattern. So this current depth increase will be the difference between those two, right? So that refers to the ratio, the increase of your energy. Right? That's related to that. So you can do this calculation, right? CD1 minus CD0 will be this equation minus this, right? And that can be simplified as that equation, right? You with me? Okay. So you can also, it's also shown in this drawing, right? This is referring to one line, right? This is one line, and they have current depth of one line, CD0, right? And if you have multiple 1, 2, 3, 4, 5, 6, 7, 8, 9, if you have 9 lines right, written in parallel, they have this cumulative energy, right, EP, and then you have the O or current depth, CD1, right? Okay. So, of course, if you then in this way you can easily calculate is how much current depth increase, right? If you choose a different scanning pattern, right? Okay, so this is a really simple example. You have to all you need to do is to find out the hatch spacing versus the beam half width, right? Right. So this is really straightforward. Just plug it in, and then you can find out CD1 and CD0. So here, this is when you know how to when you do your experiments, right? It's easier to write a sheet, right? A 2D structure, right? With this pattern, right? You have lines or more lines, and then you get your CD1, right? The thickness of your sheet, right? 2D sheet, and then you can depending on this equation, you know the CD1, and then you can calculate the current depth for a single pass, right? Because for experiments, it's harder to measure the current depth of one single line, right? So this is a quick example. In questions? Okay. All right. So that's it for the modeling of stereo lithography. Right. So if you do research on in this area, you have to make sure you know how to make this simple calculation. Right. It's not difficult at all. But it's really useful. Even though you don't use those model for actual for quantitative calculation, right? For quantitative analysis, but you can also use it to find out the relations of your print quality versus your parameters of printing, right? So, okay, that's a fundamental model, and now I want to spend some time talk about this macro stereo lithography. So we know for stereo lithography, it's quite easy to understand. Is usually people use laser, right, or DMD, which is the macro lens array, to expose your the photoresist, but it's usually limited with the resolution, right? The resolution is around a couple of hundred micrometer, right, or around maybe sub 100 micrometer. Not close to not a really high precision printing method, right? So if we are with that model, if we can shrink this half width of your laser, lower this W0, decrease this W0, we can decrease this line width, right? We can also control the current depth, right? If you go back to revisit those equations, so that means if you want to increase the resolution, which means smaller, narrow line width, right? You want to be able to write really thin line. This is also a strategy from the MEMS industry, right? Whenever you want to make a circuit, right, or a sensor, any other electronics, you want the building unit to be really small, right? That means you want to make a really thin line, right? So there's of course there's a need for in the MEMS industry, right? In the MEMS industry, people are still focusing on 2D patterns, right? So for the chips, the CPU, the chips in your cell phone, they're all 2D structures. There's no 3D structure, or at most 2.5D, right? They may have different layers of 2D patterns, but usually it's really hard to get a 3D structure, right? So if we want to use our 3D printing technique in those high-tech area, right? For those applications, you want to increase the resolution. So there's a need for the MEMS industry, for the silicon industry, right? So it's not that close. It's really hard to compete with them. But 3D in terms of 2D, you can have different device design. You can have more freedom, right? And because of that conventional, the limitations on conventional processes, right? So, but we will have to be realistic. In order to compete with those 2D, those conventional processes, it's really difficult, right? You have to go down to nano scale, right? But we have to take a small step, right, to work on the macro scale lithography first, rather than nano scale lithography. Of course, you can have two methods, right? One is using the laser beam. Of course, now you have to focus your laser beam. Another one is to use the dynamic mask method, DMD, right? So similar as our regular SLA process, right? So difference is that we have to focus the laser or have a smaller image of this DMD image, right? Now for this projector, you have this optical system to enlarge your image, right? But for our macro scale lithography, we're not going to enlarge our image. We want to try to focus the image. So that means you have to modify your system, right? So to modify your system, you have to firstly understand really well of your existing system. Right? So for the classic processes, we have this UV laser, right? You have shutters to control the light path, right? And you have this optical parts to control the laser to make it we call it to usually you have a pinhole, right, to make sure your laser be a high quality, because the laser from the machine, right, from this purchase laser may not be of that high quality. Usually you have to go through a really small pinhole to get a Gaussian shape distribution, and then it goes through this XY mirrors to control the scan of the laser, right? First, this is to control the XY coordinates, and this stage you can move it in terms of Y axis. So if you want to use it for macro steering software, what kind of modification you have to do?
Spot size.
To focus is spot size, right? You want to add in some optical elements, right, to focus it. The lens, maybe not simply with one lens, right? Array of lenses, but actually the goal is to minimize the spot size. What else? Is that all? If you want to develop this machine? Yes. So even though the line width can be really thin, right? But if the resolution x, y, and z axis, if those moving resolution is not high enough, what's the point, right? So you have to increase this location in resolution, right? X, y is controlled by the mirror, right? So this is a little bit tricky. You can, because it depends on how much rotation you're applying to the mirror, right? It's really sensitive to that degree, to that angle. So you may have to use a finer step model to control the rotation of the mirror, right? To have the macro steps, and also z-axis, right? Usually you have this mechanical linear rail to control the z-axis, and that resolution is usually limited to around 50 macrons, right? So if you want to have if you have a thinner current depth, right? If you have a current depth less than 50 macron, you have to modify this z-axis, right? So you need to calculate this current depth to make sure you can work with that. There's a need to modify this z-axis. Okay, so this is for the laser scanning, right? If you have a DMD, the other process type, right? If you have DMD to expose if you are using the DMD method, you'll be quite similar, right? DMD method is easier, setup is not as complicated as this laser scanning method, right? You only have that DMD to project your image to that layer, right? So you will need to add in the focusing optical elements to focus that. But probably focus that later those spots, right, those pixels onto that image plane. You have to run optical simulation, which can be quite challenging. Right? So, and also another challenging for this focusing, right? For this focusing method, if you imagine you have this focusing lens here, and what happens to this laser spot? It may have a good focus at this position, right? But what about here? No, right? It won't be a focal point, right? So the focal point will, the ideal focal point, right, will be at this plane, right? So if you are printing in a large scale, this will give you a lot of error, right? So how to solve that? If you are good at optics, right, you can modify your optical system. Use it's called a nonlinear optics. You can engineer your focal plane to be in this plane, right? So of course you will have to. This optical system can be really complicated, right? And the cost will be much higher. And what's the other approach or other approaches? Say if you want to have a startup, right? You want to have a new machine with it's pretty low cost and everyone can purchase it. And you have to keep that in mind, right? To design your machine. You can fix the laser spot, right? You don't want if you don't scan your laser, you keep your laser spot still, right, at one location, and move this vat or the subject, right? So therefore, you don't have the problem of that scanning this focal plane, right? The focal plane problem. But there also will be some other problems, right? Because of the resin, it's low viscosity resin. If you move the resin in XY coordinate system, XY direction, really fast, right? That will the surface will not be flat, right? So there will be some trade-offs. You may have to print in a pretty low speed. So yeah, we have to be creative if you want to redesign your machine, and you will have more problems coming up, and you want to solve those problems, right? Okay, so this is a really basic Gaussian beam focusing diagram. You can focus this beam, but not to infinity small, right? It's limited, and this is called error disk. So this half width can be calculated based on the wavelength, the focal distance, and the diameter of this focus length. Right? So this is really basic of optics. So if you have those optics, you can simply calculate your focal this error disk of those focal spots. Usually those this focus lens, and this D will be given if you want to purchase one of those mirror, right? This lens, not mirror. Okay. So that's the one for laser-based system. So if you have the projection-based system, I got this from the literature. To see this, you have to work on your projection optics. You can simplify simply by focusing that image. Right? We have this focusing lens in the projector. If you reverse it, you will just focus rather than enlarge it, right? But you also have to work on the focus length. You want to make sure you have enough work distance for your machine, right? Right. So with that, you can design a pretty low cost machine, but this machine will be because of the cost of the DMD, it's pretty expensive, right? For 4K DMDs, that element may cost more than $1,000. So this setup can be quite simple, but the machine is not that not that low cost, right? And also the lifetime of those projection-based 3D printer is limited. You can only use it for probably 20,000 hours or 2,000 hours, right? Depending on the lifetime of your DMD. So that's the setup. Of course, a lot of simulations with the optical path, and if you design your machine quite well, you can achieve pretty good printing results, right? So this is from the literature published last year. They engineered that macro stereolithography system, and see this is a scale bar, 300 micrometers, right? It's not that small, but probably this line width, this width will be around probably 40, 50 micrometers, right? If you can imagine that resolution will be way better than 50 micrometers, right? Okay. So if you want to write this really fine structure, you have to get a really good resolution, right? You can still see if you enlarge it. So you probably cannot see it really well from there, but this is the way you do the print. So in this direction, you can still see this layer structure, right? So that layer structure is determined by your the current depth and your line width, right? Okay. Let's skip that. So this is a typical setup for the network field using the DMD, right? Use the imaging lens. Some simply reverse that imaging lens to project it. So it's still this technique is still limited in research labs, not not yet commercialized. But see, if you can commercialize it, the cost won't be that high, right? And it can be really impressive. So this is the modeling of this the projection-based stereolithography. it's quite similar to the one we work with laser style. I want focus that in depth on how to derive those. Oops. Every time. Okay, so we have a slightly different equation, right? Compared to pretty similar actually, pretty similar to the laser-based model, right? Because it's based on the light distribution, right? So, but for the mass projection, for the polarization, you will have individual spots, right? Individual spots to cure your surface, right? And then the total light intensity, you have to do the integration in x and y coordinates, right? You have to do the integration over x, integration over y for that total exposure, right? Right. Assuming you have the Gaussian distribution of each spot. So this is the difference. The only difference between those projection-based stereolithography versus your laser, the vector style stereolithography modeling. So the steering depth for one spot, that's the same, right? So let me see, have all right. So I just use those two equations here, not in detail. Okay. So of course, for this modeling, you want to have your irradiance model, right? What the E, especially the energy. So the irradiance model will be a little bit different compared to the laser style, right? The vector scanning stereolithography. And then you have to integrate all those points together to develop your cure model, right? Cure model, what's that cure model? Cure model is the way to find out your line width and the current depth, right? So here, you may not have the line width, right? Because you're not scanning in this way. You're only exposed by dots, right? You may want to get this the diameter of your dots, right? Right, for this cure model, you're not having this part, maybe this diameter of width, right? So the idea is the same. Then you get the dimensions of your cure layer, your pixels, the size of your pixels, right? And even the morphology of your pixels. The morphology of your pixels should be in this way, right? Like a lens, like macro lens. Okay. So that's a mass projection photolithography. Okay. And now we want to spend a little bit more time on the two-photon stereolithography. which was called the two-photon polymerization process. So this is different from laser-based stereolithography or the DMB, the mass projection-based stereolithography. Why it's called two-photon stereolithography? Because in this process, the photon initiator will require 2 photons to strike it before it can form a free radical. So you need 2 photons to work on this photon initiator to start the process. Okay? So the effect of this 2 photon requirement is to greatly increase the resolution of photon polymerization process. I focus on that a bit. Why you can greatly increase the resolution? Because let me see if I have this diagram. Okay, now. So when you want to have a 2 photon excitation for your photon initiator, right? Imagine you have these 2 lines, two photons to work on this photon initiator. You have to achieve a optimized condition to have this photon initiator to absorb 2 photons at the same time, right? So imagine this is regular photon initiator for 1 photon absorption, right? So for 1 photon polymerization, that means whenever you have the light shining on the surface, right, you will provide a lot of photons, right? Many photons, and those photons can be absorbed by the photon initiator, and that reaction will start at that time, right? So for the laser scanning or DMD, you have the UV laser. Once you have the UV laser shining on the surface of photoresist, the photopolymerization process will start, right? They may not fully cure, but the process will just start. For the 2 photon polymerization, you can control the process, right? So usually for 2 photon polymerization, you have to reach a really high intensity. Light intensity. You have to reach a really high light intensity to start this 2 photon polymerization. That means if you have to focus your laser, right? You have to quench your laser into a pulse laser so that you can reach a really, really high intensity for that polymerization to happen. So that means you can focus your laser to a really small spot, and that polymerization process will only happen at this spot, right? Not here, right? Not other not this area. You may argue that you can also focus your laser for your macro stereolithography, right? We just spent some time on that. The difference for this for the focus laser of 1 photon polymerization is that you have to focus on the surface of your resin, right? You have to focus on the surface of your resin. If this focus spot is in the middle of this resin, this area will be gradually solidified, right? Because they have 1 photon absorption, rather than 2 photon absorption. So that's the difference. That means for the 2 photon polymerization, you can have a just have a part of photoresist, right? You have a pool of photoresist on this substrate, and then you can control the focusing of this light, right, of this laser to make your 3D shape, right? You don't need to work on the surface of your resin. You don't need to recode the resin, right? You don't need to change the location. You just need to move that laser spot, the focus the laser spot. So that's the way for that's the idea for two photon polymerization. There are multi-photon polymerization process, which is similar to the two photons. It's even more difficult to start that process. Right? That means you have to absorb more photons for the polymerization. And generally, if you want to get a really high laser intensity, you have to use a pulse laser. You have to use a really high power. The laser I used was a high sapphire laser, and with that high sapphire laser, you can generate around 800 nanometer wavelengths and pulse with 200 femtoseconds. Right? We also call it femtosecond laser. That means you crunch your laser into a really small time frame, right? So which means the energy will be crunched in the small time frame. Peak power can reach 50 kilowatts, and you also have to focus it with a really high focus objective lens. Right. So this is a diagram. I got it from my paper published 2010. That's my first and second paper. So the setup is in this. We had our self-built femtosecond laser, which means we had to start with the pumped laser, 532 nanometer green laser. It's a really strong laser to heat this high sapphire crystal, and then you get this. You collect that excitation and then build that X-style chamber to generate this femtosecond laser. So anyway, you get this femtosecond laser, right? You have to modify this laser. You have to use a pinhole to make it to make it a Gaussian light, right? And you have a shutter to control the on and off of the laser. So this is the lens that can reflect light in this way and also pass the light into the monitor. So then you have a way to monitor your process. Because it's a really small scale, down to nanoscale, right? So you have to use a high, really sensitive camera to monitor this process all the time. Right? And this is usually built up in the optical microscope. And the whole process is controlled by the computer, right? The computer has to control the shuttle, the movement of this stage, right? X, Y, and Z in this direction. And this stage has to be really has to have a really high resolution, right? We had a nanoscale stage, nanoscale resolution. I think it's one nanometer in X1, X, Y, and Z directions. So it's a piezoelectric based stage. Right? So that means the distance, the total distance it can move is quite limited. I think it can only move up to 50 or 100 micron, not even close to 1 millimeter. So this part is usually built from the bottom up. You start with this substrate, right? You have to use the glass slides. You have to build it from the glass slides so that you can harvest that part. It can be you can use it for really complicated parts because it's immersed in that resin, right? And that resin is usually high viscous resin, so that it doesn't deform. So this is one. This is a really famous book that is published, I think, around 2007. It's really fascinating. I think this is 1 micron, right? 1 micron times this scale bar. So it's quite amazing to be able to produce a 3D shape at that time. Right? No other method can achieve this kind of resolution, and also for the 3D design. Right? So this is one of the kinds technique. I think until now, probably until now, right? You can never get a similar structure without the technique. Okay. So at that time, there was no company working on that those commercialized femtosecond laser system. Right. So the most important thing is to get that really high intensity pulse laser, but no company can work on that. It's really unstable. With that development of that laser, one company is really focused on the femtosecond laser 3D printing. It's called a nanoscribe, and they develop really stable laser, and they use that laser for 3D printing. I invited that a engineer a scientist from nanoscribe to give a presentation. I think 2 years ago. Maybe you have attended that seminar, but he showed us a lot of results. People use that nanoscribe system to print, right? So this is the Eiffel Tower, right? Part of Eiffel Tower, and you see this lady standing inside this Eiffel Tower, and you can enlarge it. You can still see this is the human figure, right? So the resolution is really high, and now with the development of those hybrid moving stage, right? They can achieve high resolution at the same time, large travel distance, right? So they can print a relatively large part that can be you can see it, right? Although it's still really small, really small. So, okay, this is we have covered this absorption, right? So the workflow, first of all, you have the 3D model, right? And then you have to slice this 3D model to print it. Right? First, when I was working on this machine, we have our own developed slicing tool with a short code to integrate with the AutoCAD to slice the sample. So now you have a lot of many slicing software, right? Sure, Slice 3D, and I can list that a bit later. So you can use commercial slicing software to get your slice pattern, and then generate the writing path within that each layer, right? And of course, you have to work on this hatching distance, right? It's a pulse laser still this laser, right? You can still work on that this model. steering lithography model. Right. So then of course you have to control the power to control the threshold, right, to get your final part. So the focal, the objective length, if focusing that later, it matters a lot. It determines how fine, determines your resolution. Right? If you have a really high focusing objective length, you can achieve around 200 nanometer, this nanometer, 200 nanometer resolution in XY coordinate, XY direction, but not in the Z direction. Z direction is really really hard to achieve, smaller than one micron, right? So this is the typical, almost the best resolution we can achieve. But if you use the lower magnification objective length, the resolution will be larger, right? That means the spot will be larger. The writing speed can be faster, but the resolution will be decreased, right? Okay. Some other examples, right? You see this can be used for different kinds of research, right? You can work on many different materials, acrylates, epoxies. You can work on positive photoresist, negative photoresist. Right? You can work on hydrogel. So it's almost similar to your conventional steering lithography process, right? But you have to engineer your photo initiator to be this two-photon polymerization, right? You can also I think this is a work from University of South California, and they use this for solid mechanics study in the nanoscale, and they use based on this polymer-based material, they derive the ceramic structure. Right? So it's the polymer-derived ceramics made in the nanoscale. Right? And this is the macro optics. You can also get the optics because of the high resolution. Right? Optics, 3D printing of optics is always an interest, but it's really, really hard to achieve that, right? Because if you don't have a smooth surface, right, you won't be able to get a good quality of optics, right? Depending on the wavelength you're trying to use, usually a couple of 100 nanometers, right? For example, 500 nanometer wavelength of light. You want to focus them, the surface roughness has to be much lower than 500 nanometer, right? Presumably to be lower than 100 nanometer. So no other 3D printing methods can get this high resolution, but this two-photon polymerization method can get this macro length, right? So this is also made by myself. I was at that time I was working, try to work on the macro length array, and see we try to tune the writing pattern to increase the resolution, right? Because the layer thickness, if you go to the top, you will be able to see this stats, right? This individual stats, because the curvature, this angle will be larger up to the top, right? So we have to increase that. We have to decrease this layer thickness up to the top, while keep the bottom part larger, right? To speed up that printing process. So see, this was done 10 years ago, right? So there are a lot many new publications published in this area. Now that people may use it for different applications, but in terms of printing techniques, it's still I think it's still developed at this stage, right? Not much of advance until now. Right? So I think this also provides you a one sample topic, right, for your final for your paper presentation, but for your group project, right, for your final project, this is not a good topic to work on, right, because we don't have that femtosecond laser 3D printer, right. We may have a femtosecond laser here, but it's not used for manufacturing. So many interesting techniques out there, right? I think we have to be proactive and search for them, right? So that concludes all on the stereolithography. I feel like this macro stereolithography is the way to go because it's cheap, it's fast, and also high resolution, right? Also, it's possible to for a company to provide the consumer style, consumer grade printer, right, in this macro scale resolution. So that would be can be the opportunity for you. Okay, questions now? I think you all have submitted your model, right? I will go through the model and then we're going to print it out. So for the printing process, I will introduce a little bit this Friday, right? How this printing process goes through, right? What kind of software are you going to use? I assume you all know how to use the 3D modeling software, right? So I focused on introducing those slicing software and those parameters you can set up for in your slicing software and also for the printer setup, right? Okay, so it will be quite straightforward but fun.
Are you just using Cura for the slicing software?
You can use Cura, but you can use other software, right? I think it's Slicer 3D. Is that Slicer 3 or Slicer 3D? That's a Slicer 3. That's an open source software that's also quite powerful. Cura is really straightforward. You don't need to tune a lot, and you can get a good G code, right? Working G code. So yeah, if you are not experienced, you can use. I would recommend you to use Cura. But if you want to have more control, you can take a look at the Slicer 3D, Slicer 3D. So there are a lot of really helpful documentation online. I recommend you to do your self-study on that, right? I try to not cover those details, right? Technical details, because it will change day by day, right? So what I'm teaching here, trying to focus on the fundamental that can be useful for you, maybe for a couple more years, right? Okay. All right, questions? No. So for those who haven't decided the schedule, right? Please come forward to make a decision. And I assume the first presentation will be on March 6th, right? So please plan ahead, right? Okay. All right. Thanks.